So now let's use what we've learned to troubleshoot a circuit here. And by troubleshoot, I mean determine if there's a problem, and if there is, what that problem might be. So the best way of doing this is just to practice and to think through what the relationships of the voltages and currents in series and parallel really should be. So let's look at our circuit here. So we've got an ammeter in the circuit. That's what this is, and it's measuring 3.5 milliamps of current. And then we've got a voltmeter way out here measuring the voltage across my 4K ohm resistor, and it's measuring about 6 volts. So the question is, are these readings correct? All right, well, let's start with our voltage measurement out here. We're reading 6 volts across the 4K ohm resistor, and notice that the 4K is connected to the 3K and the 6K ohm resistor, and also the voltage source on the top, and it's also connected to those resistors and the voltage source on the bottom. So that means that the 4K ohm resistor is in parallel with the 6 volt source. So yes, it really should read 6 volts. So we're good there, right? Now, what about the ammeter reading? Is the current reading right? Well, let's just talk about what we should see there. So here we've got 6 volts across a 6 kilo ohm resistor. So what should the current be through here? Well, it should be 6 volts divided by 6K, which is 1 milliamp. Let me write that again. 1 milliamp here. And then we have 6 volts across our 3 kilo ohm resistor. So what should the current there be? Well, 6 volts divided by 3K would be 2 milliamps. Okay, so we've got 2 milliamps there. And then what would the current be through our 4K ohm resistor? Well, we've got 6 volts divided by 4K. So that should be about 1.5 milliamps. So how does that help us? Well, we know that the current supplied to all of these branches should be the sum of all of that current. So I sub S should be 1 milliamp plus 2 milliamps plus 1.5 milliamps, which is what? 4.5 milliamps. And yet I'm only reading 3.5 milliamps. So what do you think might be the problem? Well, it kind of looks to me like with 3.5 milliamps, it looks like we might be seeing the 2 milliamps here and the 1.5 milliamp here, but we're missing maybe the 1 milliamp through the 6K ohm resistor. So what could be happening there? All right, in order to figure this out, let's talk about a couple of things you may not be familiar with yet. And that's what we call open circuits and short circuits. So open and short circuits can be caused by many different reasons. And this is a lot of times what's wrong in your circuit. You'll either have an open circuit somewhere or a short circuit somewhere, causing the circuit not to work as expected. So let's talk about what an open circuit is and what a short circuit is. An open circuit means that you have 2 terminals somewhere in your circuit that are not connected at all by an element, by a wire, by anything. And basically what that means is there's no path for conducting our current, so the current through an open circuit is always 0, right? If there's no path for that current to flow, the bridge is out, so to speak. There is no current through that wire or through that portion of the circuit. There can be a voltage across there, okay? Remember, a battery all by itself is an open circuit. There's no current flowing through there until we connect it to something, but there is a voltage there, right? So an open circuit can have a voltage difference across it, but it has no current, and that's pretty much the definition. So for instance, we might have a system here, nothing connected between these terminals basically means there's no current through there. And that's the important thing to remember with an open circuit. no current at all, I equals 0 amps. Now there might be a voltage across here. So what that might look like in a circuit is that you have a voltage supply here and no connection to get back from the positive terminal to the negative, and that's an open circuit. So here we would actually see no current through here, but if we connected our voltmeter, just imagine this is our voltmeter here, and we're going to connect the red lead here and the black lead on this side. So basically what you would measure on this side is plus E, and on the black side you would see V equals 0. So the voltage, the open circuit voltage, would just equal E, whatever your supply voltage is there. Okay, how would we get an open circuit? Well, we have these things we call fuses, and you'll see those in your circuit. There are several in your car, for instance. So a fuse is actually an overcurrent device. It actually looks for a time when you have more current than you need to have in your circuit. And what it's going to do is that element, that piece of metal inside, is going to heat up and burn away so that it opens the circuit. This is to protect the rest of your system so you don't send too much current to an element that cannot handle it. Okay, so in this case, that's a good thing that you would have an open circuit, right? It's protecting the rest of your circuit. Okay, another reason might be that you lose a connection in your circuit due to some wear. Like this is from a flashlight, so the contacts between the battery and the bulb get bent to a point where they don't make good contact anymore. So to fix that, all you would have to do is pull out the contact a little bit so that it makes good connection with between the battery and the bulb, which is what you're trying to supply the current through. Another thing you probably have noticed, if you have series lights, like Christmas lights, if one bulb burns out, what happens to the rest? It stops the current flow through the rest of the circuit, and actually none of your bulbs will work at that point as well. So that happens as well when you have a bulb that burns out. Now, a short circuit, by contrast, is a place where you have low resistance between two terminals in your network, usually where you don't intend it, right? So that would be a short circuit. So in this case, you see a short from those two terminals, meaning you have current through there, but you don't have a difference in voltage from one to the other. You don't have any resistance or very low resistance. Okay, so a short can carry a current of a level that's determined by the circuit, but the voltage across the terminals is 0. All right, so let's see how this works. So in our open circuit, okay, so let's talk about how this open and short circuit thing works. So in our circuit here on the left, you see that we have a 10 volt source we've applied to a 2 ohm resistor. So that means that we should have 5 amps of current through the circuit. Now we've given this circuit a 10 amp fuse, so that only in the case where we see more than 10 amps do we have that fuse break or open up so that we stop the current flow. So as long as this circuit stays the way it is, we're fine. We're under the 10 amps and it's not going to open up, and we're going to supply that resistance with 5 amps and we're good. Now, in the second circuit, what happened is, for some reason, we have shorted out that resistance. Okay, and what I mean is we have some other wire or some connection from one end of the resistor to the other that is 0 resistance or extremely low resistance. So basically any current that would be coming toward that resistor would then go around the resistor and back to your source, okay? And it would skip your resistance completely in the circuit, okay? Now the problem with that is that without resistance, our current would just grow and grow and grow, and it would not be limited in any way. The resistance actually limits the current in our circuit. So what happens is, at some point we get a current as greater than 10 amps, And what happens is that's going to open up our fuse, and all of a sudden, once that opens up, we have zero current. Okay, so basically the short circuit caused that condition where we were growing that current unbounded, and then the fuse opened up to protect the current because of something else that happened. Now, how do we have a short circuit? Well, there are several ways this happens. For instance, you might have two terminals really close together, and one wire from one terminal comes over and makes contact with the other terminal without you intending for some reason. You could have twisted wire here that either that maybe the insulation gets pulled off of some of the wire, and they touch, because these are two different wires that aren't supposed to touch. Maybe the insulation gets pulled away and they connect inadvertently. Maybe you've got a very tight winding that leads to a short circuit there. So let's do a little bit of circuit analysis here and talk about what's going on in these two circuits, for instance. So in the first circuit here, we have an open circuit between A and B, the terminals A and B. And there's really no path in this circuit for current to flow, right? So I is equal to 0 amps. No current at all. So what's our voltage drop across R1? Well, that would be I1 times R1. So if current is 0, it doesn't matter what our resistor value is, we have no voltage drop there. Okay, so I'm going to say 0 volts there. Same reason we've got 0 volts across R2, because no current through there means no voltage drop. So what does that mean? That means that at point A, we're basically just connected to our voltage source, and at point B, we're basically connected to the negative terminal of our voltage source or to ground. So VAB in this case would simply be the source voltage, or 20 volts, where our current would be 0 for our open circuit here. Now in our second example, we have a similar situation, right? We've got no current because, again, there's no complete path to get from the positive terminal of our source back to the negative terminal of our source. There's just no complete path for that. So that means that there's no voltage drop here across R1. There's no voltage drop here across R2, right? Because there's no current through either one. So for both of these, we might as well just be measuring, just have a straight wire in here. There's no difference, right? And I'm going to kind of just draw that wire here. So we're skipping over the whole resistor here. And then I'm going to give that its own color out here. And let's try to determine what VAB is. Right here, measuring our voltage from A to B. So remember, our V equals 0 down here at ground or at the negative terminal. And what is it at A? That is 10 volts. Okay, so VAB is the same thing as VA minus VB, where VA is 10 volts and VB is 0. So we're going to measure 10 volts there. Okay, now let's look at the voltage across here, VCD. And again, same thing, when you have the double subscript notation, VCD is VC minus VD. So we just have to figure out what the voltage is at C and what the voltage is at D. So down here at D, V equals 0 because that's still connected to the negative terminal of that 10 volt source. And actually, I'm just making an assumption that our ground node is down here. So what is the voltage up here at C? Let's think about that for a minute. We've got 10 volts here on this side of E2. And what happens from here to here is we have a drop of 30 volts. So 10 minus 30 means that we'd have a negative 20 volts right there. And if we just plug that in, we've got negative 20 volts minus 0, VCD must be negative 20 volts. Now, when you see a negative sign in our voltage, what it means here for us as far as VCD is that it's really a drop from here to here of 20 volts. Okay, so we're at a higher potential down here at ground than we are at point C. Okay, so let's scroll down and look at our circuits here. So for circuit A, what's going on here is we have 12 milliamps coming in, and then we should see that current divide, right? We should see some current here, here, and here. However, notice that this portion of our circuit out here has no resistance at all, okay? And it offers that 12 milliamps a path around any resistance, okay? So what we're going to see is all 12 milliamps go this way because we've shorted out both R1 and R2. So we're going to have all 12 milliamps this way and 0 and 0 amps here. Okay, because we've offered, like I said, that 12 milliamps has a path to get back to the source without encountering R1 or R2. It can go around, and current always takes the path of least resistance. Okay, so we're going to see that 12 milliamps back over here, having not had to divide through our circuit. And what about our second circuit here? Here we have, normally we would see current leaving the positive terminal of the source and returning back to the negative. However, in this case, there's an open in the circuit. So basically, if we had any current, it couldn't jump that across those terminals. So the bridge is out, so to speak. So this is what we would call our open circuit, where we would have a voltage but no current. Okay, so I is equal to 0 throughout our circuit. So that means there's no voltage drop across R1 and R2. So it's as if those resistors don't exist. So on this side, we would see 22 volts. And on the other side, we're connected to ground, so we would see 0 volts over here. So our open circuit voltage would just be the 22 volts that we see across the source. Okay, let's look at this circuit. This is an interesting circuit. So here, do we have a path for current in our circuit? We actually do. If we have current that leaves the positive terminal of our source, it actually can go this way and get back. Okay, so we would not have any current this way, because we've got this open circuit over here. So what we want to do is figure out what would our open circuit voltage V sub L be in this case. Okay, so first thing to recognize, if there's no current through the 3.3 k ohm resistor, then we would have no voltage drop across it either. And this might as well just be a wire that we're measuring straight from here to here. So when you look at it this way, V sub L is actually the voltage across that 4.7 kilo ohm resistor. So then this turns into a simple series circuit where we can find our RT, and RT would just be the 2.2 k ohm resistor plus the 4.7 k. Now I'm adding these because in this, without the current going through the 3.3 k ohm resistor, the 2.2 and the 4.7 are in series. And remember, to find RT, we add those. So we have 6.9 kilo ohms of total resistance, meaning our source current would be 9 divided by the 6.9 k. Or 1.3 milliamps. Okay, and that 1.3 milliamps is actually the current that continues this way through the 4.7. So the voltage drop across my 4.7 would just be the current through the resistor times the resistor value. Again, just Ohm's law at this point. Which should be about 6.13 volts there. So 6.13 volts here, and that is my open circuit voltage VL. Now let's look at one more example, and this one's kind of a challenging one. So what's going on in this circuit? Well, we've got an open circuit over here, so there's no current right here. So I would say I equals 0 right here in the circuit, right? So we've got a short across my 10 ohm resistor. So any current that would be going through here would go this way. However, once it got over here, where's it going to go? It has nowhere to go, so we're not going to see any current through here whatsoever. So basically, the current this direction would simply be 0, okay? No current there at all. So that means that here, and there's no current through that 5 ohm resistor either. So that means V2 would just be measuring across my 20 volt source, and I2 would just be 0 amps. Again, because there's no path. If the current went through I2, that's fine, but it would have nowhere to go. So the current wouldn't even go through I2 to start with. So that means that whatever our source current is, it would go this way through our 4 ohm resistor. And let's make sure there's a path to get back to our source. So we'd still see that I sub s here. And then what would happen when we get to this point? Well, if we had a resistor over here, we would divide the current through those two resistors. But since we have no resistance over here, R equals 0 ohms on this side, our current would just continue this way. So our source current with no current going through the 6 ohm resistor at all. Okay, so if I equals 0 here, that would mean V1 also equals 0 volts, right? 0 current through the 6 ohm resistor just equals 0 voltage. All right, so what does this tell me? I'm going to get rid of some of this. This tells me that the path of current through my circuit looks like this. It's going to go this way and then return back here. So that's my circuit. If you wanted to draw it, if you wanted to draw this, it would just be a 20 volt source in series with a 4 ohm resistor. So RT would be 4 ohms. I sub S would be 20 over 4, or 5 amps. which means I1 would be 5 amps. And of course that would give us a 20 volt drop again across the 4 ohm resistor. So V1 would be 0 because no current would go through the 6 ohm resistor. V2 would be 20 because there's no current through the 10 ohm or the 10 ohm or the 5 ohm resistor, so we're just measuring across our voltage source. I2 would be 0 amps because we have no current going toward that side of the circuit because it's open over there. And then I1 is 5 amps. That's all of the current of the circuit, the 20 volt source across the 4 ohms of resistance. Okay, so going back to our original circuit where all of this started, let's see if I can get all the way back up there, where we started talking about troubleshooting. So what we think is happening in our circuit is that it would appear, since we see, let me get rid of some of this, since we actually do see the 2 milliamps and we see the 1.5, it looks like what we might have here is that our 6K ohm resistor might be open, okay? Because if it's open, then this 1 milliamps won't be pulled from the source at all, and we'll just see that source supplying the 2 milliamps and the 1.5 milliamps. If the 6 kilo ohm resistor was open, that would then take all of that current. We wouldn't see current through the 3K or the 4K, and we would see a no voltage across the 4K. So it's very likely that what we have here is an open circuit across that 6K ohm resistor.